And the title is Polynomial Optimization of Stable Sets in Graphs.
Okay, thanks for the introduction. Yeah, so this is a joint work with Monique, she's my supervisor, and also with Marcus Beckhofer, that we worked a couple of months ago in a second-hand instance. Okay, so the main players of this talk are going to be these two objects, the stability number of a graph and the compositive cone. So let me start by defining the stability number of a graph. So if we have a graph G, a subset of vertices S is stable if S contains no H, and the stability number of G is denoted by alpha of G is the maximum cardinality of the stable set. So for example, in the Peterson graph, the stability number is 4, and you can check that the red set is stable, and you cannot find one stable set of size 5. One way to see that is in the 5 cycles. You cannot. So the stability number of a 5 cycle is 2. So computing the stability number is an NP-complete problem, and we would like to study some approximations for this. So on the other hand, the compositive cone is the set of symmetric matrices such that the form X transpose MX is non-negative for non-negative vectors. Here, non-negative vector, I mean entry-wise non-negative. So we can formulate equivalently in the second way, like the compositive cone is also a set of symmetric matrices such that the polynomial X squared transpose MX squared is non-negative on Rn when X squared is the vector of a square of the variable. So basically, in the second definition, what we are doing is encoding the non-negative to the variable into the variables. Of course, these two definitions are equivalent, and optimizing over the compositive cone is hard, as many hard combinatorial problems can be included as an optimization for a COP-N, and even determining whether a matrix is compositive is hard. In this talk, we're going to study some certificates for compositivity that are based on sum of squares of polynomials. So these two objects, or these two topics, meet by the following formulation by the Clerk and Pasechnik in 2002, following one result by Motzkin and Strauss, is that the stability number of a graph can be formulated as a linear program over the compositive cone in the following way. So alpha of G is the minimum T such that the matrix T times AG plus I minus J is compositive. AG is the adjacency matrix of the graph, I the identity, and G the odd ones matrix. So by this formulation, then if we put T equal to alpha of G, and this is compositive by the formulation. So this is what this is saying is that the matrix NG equal to alpha of G times AG plus I minus J is compositive always. And this is a matrix that is going to be important that associated matrix to the graph. Okay, so now I would like to, so everybody said that certifying or deciding whether a matrix is compositive is a hard problem. We're going to study how to certify. Okay, so I like the second definition that I used. So the compositive cone as the set of symmetric matrices of this associated polynomial is non-negative over Rn. Okay, so let me define what the sum of squares is. I suppose everybody knows. So P, a polynomial P is a sum of squares of polynomial. I write SOS if P can be written as a sum of squares of other polynomials. So, and then in particular, a polynomial is a sum of, if a polynomial is a sum of squares, then it's non-negative. And then if the associated polynomial of the matrix M is a sum of squares, then M is composite, just by definition, right? And then we ask the question: does every compositive matrix give one sum of squares as an associated polynomial? And this is true for matrices up to size 4. So if you have one compositive matrix of size 4, then the associated polynomial is a sum of squares. But this does not happen for n equal 5, because, for example, the Horn matrix is a compositive matrix for which the associated polynomial is not a sum of squares. But Parrillo showed one elegant proof for showing that H is a compositive matrix in the following way. So the associated polynomial of H is not a sum of squares, but when multiplying by the sum of the squares of the variables, it becomes sum of squares. So then this polynomial is a sum of squares, in particular non-negative, and the first factor is positive. So it implies the second factor should be non-negative, so H is composite. So this is also like a sum of squares certificate for compositivity purposes. So then we can consider then the more general certificates of this type in the following way. So we say that the matrix M is SOS certifiable if the following polynomial is the sum of the squares for some r. So the sum of the squares of the variables to some power r times the associated polynomial is the sum of the squares. So by the same argument as in the previous slide, if M is SOS certifiable, then M is copositive. Because if M is SOS certifiable, then this matrix is, this polynomial is the sum of the squares, and the first factor is positive, except on 0. It's positive, it implies the second one should be non-negative, so the matrix is copositive. So we know that if a matrix is copositive of size 4, or 4 by 4 copositive matrix, then it's SOS certifiable because it's already a sum of the squares with r equals 0. And if a matrix is in the interior of the copositive cone, that means the only 0 of this polynomial is the origin. Then M is SOS certifiable and follows by the Polya theorem, or the Resnick theorem if you want, but by the Polya theorem already shows that says that if you have one homogeneous polynomial which is strictly positive on the non-negative order, except on 0, then the polynomial multiplied by some power of the sum of the variables has non-negative coefficients. So then if you square the variable, for example, then it shows that if M is in the interior of the copositive cone, then it's SOS certified. And then based on that certificate, Parrillo proposed the cons K and R for approximating the copositive cone. And it's the cone K and R is the set of symmetric matrices that are SOS certifiable with the power R. Yeah, so it's kind of a hierarchy for SOS certifiable polynomials. So in other words, M is SOS certifiable if and only if M belongs to some of the Parrillo cones or belong to the union of the Parrillo cones. Okay. So then we have the following questions. Are all copositive matrices SOS certifiable? And this is motivated by the following. Okay, so now I'm going to talk about the stability number of the graph. And some conjectures are related to the question that I placed before. So we have the formulation of the copositive cone of alpha. So alpha is the minimum t such that matrix t times AG plus I minus J is copositive. And we have the Parrillo cones. And then use this relaxation for the copositive cone. The Clerk and Pasechnik proposed the following hierarchy for approximating the stability number of a graph. So just by replacing the copositive cone by the subcone K. And then there are some known results. For example, it's a hierarchy of approximation in the sense that if R increases, then the bound gets better and better, and that's because just because K and R is contained in K and R plus 1. And also we have asymptotic convergence, so theta R converges to alpha as R goes to infinity, and we ask, does finite convergence hold? It's one open question. Also, the bound theta 0, so when R is equal to 0, is equal to the lowest theta number plus adding one non-negativity constraint. And also, the Clerk and Pasechnik show that theta R is between alpha and alpha plus 1 for R greater than or equal to alpha squared. And they conjectured that the hierarchy converges to alpha in finally many steps, but more than that, in alpha minus 1 steps. So they conjectured that theta alpha minus 1 is equal to alpha. So in other words, what this is saying is that the matrix Mg belongs to the Parrillo cone at level alpha minus 1. So Mg is a copositive matrix, for which we don't know even if it's SOS certifiable. They conjecture that it's in the Parrillo cone at level alpha minus 1. There are some known results about this conjecture. So for example, the conjecture is true it holds for perfect graphs with R equals 0, and also for odd cycles are the complements with R equal 1, and it's also known for graphs with a stability number at most 8. And in this talk, we're going to show that we have finite convergence. We have finite convergence of this hierarchy. In other words, what we are going to show is that the matrix Mg, this matrix, is SOS certifiable for any graph. Okay. Okay, so recall. So M is SOS certifiable, right? Again, the definition, if the following polynomial is a sum of squares for some R. Okay, so the associated polynomial of M times a power of the sum of the squares of the variables is sum of the squares. And the problem we want to solve is that given a graph G, we consider the matrix Mg, which is copositive. We want to show that Mg is SOS certifiable. That everybody said that this is true. This is what we are going to show, but we need to prove it. Perfect. But then we can ask the question: are all copositive metrics SOS certifiable? Maybe this more general result hold, and then Mg is SOS certifiable just as an answer of this more general result. There are some related results to that. For example, where I already said that every copositive metric of size 4 is SOS certifiable. That's true. And also it was shown that the copositive cone is not equal to a single Parrillo cone. Actually, like in the last months, there was shown a more general result that says that the copositive cone of size 5 is not the projection of a spectrahedron. In particular, this shows that this cannot be shows the result. And it was shown that every 5x5 copositive matrix with an all ones diagonal is SOS certifiable. That's also true. And it was conjectured that every copositive matrix with an all ones diagonal is SOS certifiable. And observe that this conjecture would imply that Mg is SOS certifiable. Because the matrix Mg, if you look at the diagonal, is equal to alpha minus 1 for, so all entries in the diagonal are equal to alpha minus 1. So if you divide by alpha minus 1, is somehow an all ones copositive matrix, and then this weaker result, weaker than this, I mean, would imply our main question. But we can show actually that that's not the case. We can show that that there are copositive matrices that are not SOS certified in the following way. So if you have a matrix M which is copositive, and we assume that M is not in the cone K and 0, so it means that the associated polynomial is not a sum of squares. For example, the Horn matrix. If you take M, the Horn matrix is copositive and not sum of squares. Then when adding one zero-row column, then this matrix is copositive and not SOS certified. So this is showing that there are 6x6 copositive matrices that are not SOS certifiable, for example, by taking M equal to Horn matrix. And moreover, we can show that this other matrix, so M, so the direct sum with 1 minus 1 minus 1, 0, is also a copositive matrix and not SOS certifiable. So this is showing that there are copositive matrices with an all ones diagonal that are not SOS certifiable for N at least 7. So if you take H, the Horn matrix is a 7x7 copositive matrix with all ones diagonal, which is not SOS certifiable. So such a general result that does not hold. So for showing that Mg is a SOS certifiable matrix, then we need something else because there are copositive matrices which are not SOS certifiable, even with an all ones diagonal simple. Okay. Oops. Okay. So our main results again. So we show that if we have a graph, then Mg is SOS certifiable. In other words, we are showing finite convergence of the declared processing hierarchy to alpha. And the other main result that we show is that every 5x5 copositive matrix is SOS certified, which was the remaining case, right? Because for a 4x4 copositive matrix, the associated polynomial is always a sum of the squares, so in particular SOS certifiable, and there are 6x6 copositive matrices which are not SOS certifiable. So it's really the remaining case. And the main idea is using other sum of the square certificates for copositivity based on Lasserre type sum of the square certificates. Okay. Yep.
It's a little bit tricky. So does this mean that you have finite convergence, but somehow the amount of the number of steps in the hierarchy is not bounded?
Exactly.
Is that what's happening here?
Yes.
I see.
Yeah. So it was shown that the copositive cone of size 5 cannot be equal to a single KR, but is equal to a union. So you have to use all of them. Yes. Okay. Okay. So now we're going to construct another type of certificates based on Lasserre, on the Lasserre hierarchy somehow. So we have the copositive cone, which is the set of symmetric matrices such that X transpose Mx is non-negative for non-negative vectors, right? That was the definition. But then since the polynomial X transpose Mx is homogeneous, we can assume that, or we can restrict ourselves to with the sum of the entries equal to 1. So no negative entries, but no negative entries with sum equal to 1. And we say that the matrix M is delta certifiable if we can write X transpose Mx in the following way. So a sum of squares plus a sum of xi sigma I, when sigma is the sum of squares, plus a multiple of the polynomial for the ideal constraint of the series. So just a multiple of the sum of the variables minus 1. So why this is a certificate that M is copositive? Because if we can write the polynomial like this, and then we take a point in the simplex, then this polynomial is going to be 0. This part is going to be 0 because it's in the simplex. This one is going to be non-negative because xi is going to be non-negative because it's sum of squares, and it's not negative everywhere. So it means that this polynomial is non-negative on the simplex, which is the definition of being copositive. In a similar way, we can construct the so consider the definition with the square. So a copositive cone is a set of symmetric matrices such that the associated polynomial x squared transpose m x squared is non-negative for all x in the unit sphere. So again, not for all x, but now we normalize and then we assume that the sum of the squares of the variables is equal to 1. And then m is S certifiable if we can write the associated polynomial as a sum of the squares plus something in the ideal of the sphere. Okay, and the idea is the second. So you can write this polynomial like this, and I take any point in the sphere, then here is 0 and here is non-negative, so it's opposite. Okay. And then the interesting part is that we can link these certificates. We have that M is delta certifiable. If M is delta certifiable, then we have that M is S certifiable, and this is equivalent that M is SOS certifiable. So this part, actually the hard part of this theorem was shown by De Clercq, Monique, and Parrillo in 2002, which is this part. And we extend a little bit. I didn't put the full result, but this is what we are going to use. Okay, so we can link this sum of square certificates, and then we are going to use them in order to show that our matrix MG is SOS certified. Okay. So then the first idea is going to be we are going to try to find sufficient conditions so the matrix is delta certifiable that would imply that it's SOS certified. Okay, so first of all, we can assume that M is in the boundary of the copositive cone. Because if M is in the interior of the copositive cone, then it's SOS certifiable and delta certifiable, or by the Resnick theorem, Polya theorem, Putnar's theorem, any positive Selin set will prove that. And then we can, what it says, if M is in the boundary of the copositive cone, then this is saying that the following standard quadratic program has minimum value, optimal value equal to 0. Right? So the minimum of X transpose Mx, or the standard simplex is 0. So we have 0, and then we consider the corresponding Laser hierarchy, which is a bound for the optimal value. And then one fact which is very easy to show, actually is just writing down the definition, is that M is delta certifiable if and only if we have finite convergence of the Laser hierarchy. So then we would like to understand when this hierarchy has finite convergence in order to obtain that a matrix is delta certifiable. And for that, we are going to use a result by Marshall and me for give sufficient conditions for showing finite convergence of Laser hierarchy. So we have a general polynomial optimization problem, so minimizing fx such that the gi of x is non-negative and hj are 0. Then we would like to minimize fx. And then we have there's the following theorem that follows from Marshall, resolved by Marshall in 2009 and me in 2012. That if the Archimedean condition holds and the classical optimality conditions hold at every global minimizer, so the constraint qualification, the strict complementarity, and the second order sufficiency conditions hold at every global minimizer, then the Laser hierarchy has finite convergence for the problem for the polynomial optimization problem. Okay, so we have this result, but this result, as a warning, is this result can only be applied if the problem has finally many global minimizers. That's because the second order sufficiency conditions said somehow that the minimizer should be isolated, and then since the Archimedean condition holds, then we are in a compact set, and if it holds at every global minimizer, it implies that there are finally many. So it has it's a nice theorem, but has a restriction that can only be applied when finally many global minimizers. Okay, but then we can try to apply it, and then we apply it. And then we obtain this partial result. So if we have G1 a critical graph, which a critical graph means that if I delete an edge, any edge, the stability number is going to be the same, then the matrix MG is delta certifiable and therefore SOS certifiable for acritical graphs. So some examples of acritical graphs are even cycles, the Peterson graph, and this, or also the Kneser graphs are acritical. So it's like a class of graphs for which there are many of them. And the key fact for that is that the form X transpose MX has finally many zeros, minimizers of zeros in that case, if and only if G is acritical. So we have a characterization of the minimizers, and we have finally many just in the case, precisely in the case when G is acritical. But the situation is even worse because we can also show that if G has critical edges and is not the complete graph, then MG is not delta certified. Okay, so we can show that in the case of acritical, we show that it's SOS certifiable by showing that it's delta certifiable, but this idea can only be used for the case of acritical graphs because of the following line. If it has critical edges, then it's not delta certifiable. I would like to show that it's SOS certifiable, which is okay. And also we can apply the result of Marshall and Lee in another setting, and then we get the following reduction for the other main result. So every 5x5 compositive matrix is SOS certifiable if and only if the diagonal scalings of the Horn matrix or the matrix of the form DHD is SOS certifiable for all positive diagonal matrices. So we would like to prove that every 5x5 compositive matrix is SOS certifiable, and we will use the problem just to look at the diagonal scalings of the Horn matrix. So the Horn matrix really plays a crucial role in this question. And for this, we use a characterization of the extreme rays of the compositive cone of size 5 that they were fully described by Hildebrand, a remarkable result. And in that case, every extreme matrix that is not a diagonal scaling of the Horn matrix is delta certifiable. We can show that, and therefore SOS certifiable. And for this, we use the sufficient conditions by Marshall. But again, there is a warning. The Horn matrix is SOS certifiable, but it's not delta certifiable. So this idea, so if we want to show the theorem fully, we cannot use the delta certificates. We really have to go to the SOS certificates because the Horn matrix is not delta certified. Okay, so let's summarize what we have so far. So what do we have and what do we need? So we have a graph G and this associated matrix, which is co-positive. And we would like to show that MG is SOS certified. And so far, okay, so we have this result that links the certificates. And so far we have that if MG is delta certifiable, and therefore SOS certifiable for G acritical. Yeah, so the graphs for which this is delta certifiable are the acritical graphs. But
can you repeat what is J? I forgot.
Sorry? J is the all ones matrix.
All ones. Okay, all ones.
Yeah. So this matrix is basically alpha minus 1 in the diagonal, alpha minus 1 in edges, and minus 1 in non-edges. So it's just a matrix, a composite matrix with two values actually, alpha minus 1 and minus 1. Okay? Okay, so then the delta certificate is not, I mean, it's useful, but it's not enough for showing our main result. So we will show that MG is S certifiable. So that is what we want to show is that this associated polynomial to MG belongs to this set. I want to say now is sigma is the set of sum of the squares plus something in the idea of a multiple of the sum of the squares of the sum of the squares of the variables minus 1. So for this, we need to develop new tools for showing membership in preordering. And this is what we are going to do. Okay, so we want to show that one polynomial belongs to one preordering. Okay, so now it comes the theory of pure states. I'm not going to go in detail, but maybe the idea, if we have a preordering of the ring of polynomials, then and we consider the support of the preordering S, so the vectors points X for which f of X is non-negative for all f in the preordering. This is the support. So for example, in our case, we can consider, for example, the preordering, so the sum of squares plus, okay, you can imagine not 5, but n here. This preordering, and the support is just the sphere constraint. And then from a result by Bordov, Scheider, and Speichhofer, 2012, we have the following. So if we have a matrix that is, if we have a polynomial that is non-negative on S, and we would like to show that f is in T, we want to show that. And perhaps we have another polynomial U, which is in T, and have the same behavior around their zero set, and some extra conditions, then we can show that f is in the preordering. So let me explain a little bit this second condition that is a little bit vague. So we would like to have another polynomial U, which is in T, and have the same behavior. So they have the same zero set. The zero set of f and u is the same, but more than that, the behavior around the zero set should be the same. If we have such a polynomial, and we check some extra conditions which are not trivial, then we can show that f is in the preordering. Okay. So then the philosophy or the main message of this theorem is like, if you want to show that one polynomial is in the preordering, a good idea would be finding another polynomial which has the same behavior around the zero set and is in the preordering, and then we can maybe use it. Okay, so now then we show our main result that MG is SOS certified. Let me explain more or less the idea. So if we consider the graph, consider the graph H plus one isolated node. So this H plus I0 is the graph obtained by adding the isolated node I0 to the graph H. Then we have the following relation. Maybe I forgot. I forgot to write what is f of g. So f of g is the associated polynomial. So is this one. And so for a graph, fg is just the polynomial associated to the matrix mg. And then we have the following relation between the polynomial of h plus one isolated node and using the polynomial of h. Yeah. And then we are going to use the following result that says that if the following claim holds, that is that if MH is SOS certifiable, implies that when adding one isolated node is also SOS certifiable. If this is true, then MG is SOS certifiable for every graph. Somehow, if we know that when adding one isolated node, the SOS certifiability is preserved, then we have the third. Okay. But then, okay, so we need to prove the assumption. Okay. Yeah. And then if MH is SOS certifiable, what does it mean? So maybe I'm going to write here what MH is SOS certifiable if the polynomial fh times this for some r is sum of the squares for some. That's the definition of being SOS certifiable. So then we use that in order to get, so we multiply here by this polynomial, so this is the sum of the squares, and since this is also a square, then this new polynomial u is a sum of the squares, and if you look at these two polynomials are like with the same behavior somehow. And then we can show that this is actually a unit. We can show all properties, u and this polynomial have the same behavior around the zero set, and we can check also the conditions, and then we conclude that the claim is true, and then we have to make. Okay. Okay, and let me finish with the other results. So we can show also using the theory of pure states that every diagonal scaling of the Horn matrix is SOS certifiable for any positive diagonal matrix D. And this is because Okay, so we can reformulate this statement by rescaling the variables. That what we want to show is that the associated polynomial of the Horn matrix belongs to this preordain. So now not the preordain of the sphere, but the preordain of the ellipsoid, or any ellipsoid with the I positive. And for this, we use pure states. And the unit that we are going to use is the associated polynomial of the Horn matrix times the sum of the squares of the variables, which is a sum of the squares that was observed by Carrillo. And for showing that this is a unit, we need the following result that we proved before without knowing that we were going to use that. It's a little bit of coincidence. That actually the certificates for showing that the Horn matrix is copositive, we can use another multiplier. If we use not just the sum of the squares of variables, but with these multipliers of for di, if d with some condition of d, but when d is close to the vector of ones, it's a sum of squares. And then as a corollary, we obtain that every 5 by 5 positive matrix is SOS certifiable because we reduce this problem to precisely to the diagonal scalings of the Horn matrix. So in other words, we can state this polynomial, this statement in the following way. So we have f one non-negative even homogeneous polynomial of degree 4 in 5 variables, then there exists such multiplier such that f is a sum of squares. It's somehow like the Resnick theorem, but in that case, we don't need the assumption of a strict positivity. For any non-negative polynomial in that case, that certificate exists. Okay, so let me conclude. So we showed two main results. So the first main result was showing final convergence of the declared functions in the hierarchy. So in other words, we showed that the matrix MG is SOS certifiable. And the second main result is that every 5 by 5 compositive matrix is SOS certifiable. And the key idea was to link these certificates with Lasser type certificates and showing the existence of that certificate via an optimization approach showing final convergence of certain Lasser hierarchy and also by the theory of pure states. And let me comment about some open questions. So the original conjecture by the Clever-Pachachnik is still open because we need to show this with this degree convergence, also with alpha -1. And we would like to have an explanation of why we have this a combinatorial explanation for this final convergence. For example, if we have a perfect graph, it converges in one step. The R equals 0 converges. And if we have an odd cycle or a complement of odd cycle, in R equal 1, it converges. So it's like the non-perfectness, if you could think about. So it would be nice to understand for which graphs we have convergence at the R equals 0, R equals 1, R equals 2. So there's something more combinatoric from a combinatorial point of view here. And also degree bounds for these results by the end. And the second question related to the copositive matrices is, are all 6 by 6 copositive matrices with an all one diagonal SOS certifiable? This is a question that is still open and could be true. We don't know. And recently, I think that the extreme rays of the copositive cone of COP6 were characterized. So I think it's at least a question that you could try. Thank you.
Thanks. Question, comments, please.
You mentioned that possibility to represent the one of the positive matrices as a spectral shadow is somewhat related to your study.
So it was shown. It's in archive this paper now.
It's a recent, right?
It's very recent. It's June or something like that. That says that the copositive cone of size 5 cannot be represented as a shadow for spectral hidden. So it in particular showed that the copositive cone of size 5 is not equal to a single Carrillo cone, to K5R for some fixed R. But what we show is that it's equal to a union. So yeah, it's not in contradiction with the result. Yeah, but it's related.
Yeah, so is there, I mean, forget alpha of G -1 as a bound, but is there any chance that there is some bound that can be extracted from kind of like the the general pure state.
We don't know yet, so we're trying to so it's a question that we care about, but no, we don't know so far.
I see. So it's not clear that any bound can be extracted from.
Yeah, it seems that it can be extracted some bounds, but there are like two bounds, I think, like
No, I mean,
exponential.
they're going to be terrible, but I'm just curious. But I'm curious. I mean, it's not going to come close to like some.
No.
Also, it's not clear that this is the right bound. Right?
Yeah.
It's a conjecture,
That's
but,
yeah,
I'm just wondering if there's some bound, can.
Yeah, maybe. Yeah, I should mention maybe that this conjecture is motivated, but because there are other approximation, semi-infinite approximation for the stability number via 0-1 optimization and polynomial optimization or 0-1 polynomial optimization, and the behavior is alpha minus 1. So it's conjecture in the sense that maybe this continuous formulation of alpha, the sum of the squares hierarchy for continuous formulations have the same behavior as the 0-1. But yes, it could be that it's not true at all. But yeah, we don't know bounds.
Other comments? Maybe can you go please one slide back just to be sure if I understand well. So the main result too, it's true for sides up to 5, no?
Yes.
That copositive is the union of this set of parallel. If I understood, you found a counterexample that for 6 this cannot
Yes.
be true. Okay, that's interesting. So just as a philosophy, Bern made a comment that for positive rank there is a gap between 4 and 5, and for co-positive looks a gap between 5 and 6.
Yeah, also between 4 and 5 also, because 4. So if you take one compositive metric of size 4, then the associated polynomial is the sum of the squares, and it's not the case for COP5. But yeah, this SOS
allowing the denominators.
Yeah, allowing the denominators, then yes. Yeah.
Please.
Okay, so you've proven that these 5x5 co-positive matrices are SOS certifiable, but can you give me an intuition of how the spectrum goes? I assume there are ones that are easier to certify and ones that are harder to certify. Is there an intuitive way of seeing like what type of structure emerges as you go from easy to hard? Yeah,
actually our proof was looking at the extreme ratio, so we didn't really look at the specific matrices somehow. But there is a previous result that says if you have one 5x5 compositive metric with diagonal 1, with all ones diagonal, then it's SOS certifiable with R equals 1. So just multiplying by the sum of the squares variables becomes sum of the squares. So maybe this is like the easiest kind of 5x5 compositive metric.
Okay. Sorry.
So you use this so you say it should be similar around the zeros.
Yes.
What is it? So Taylor expansion to order 2 or is it more?
Yeah, so it should be I think the second derivative, like up to the second derivative. It's not like a condition that is it's a condition that follows from another condition. It's not it's not the right condition to check, but
it's not linked to the multiplicity.
Also, so the multiplicity of the minimizer should be the same. It's like really the minimizer should be like the same with the multiplicity and also like with the second derivative. Yeah, so in this case, for example,
So
the zeros of this polynomial and the zeros of this polynomial are clearly the same because it is positive. Yes.
Okay, so the local wings should be equal.
I'm not sure something like that, but yeah, maybe I'm not sure.
Okay. So we thank